So in the last video, we saw this function v, which computes the solutions of a given set of polynomial equations. And we saw that the solution set really only depends on the ideal generated by the set of equations. And so we did obtain a map, taking an ideal in this polynomial ring and sending it to the set of solutions, which is exactly the definition of an affine variety in this affine space. And so we have this map in this direction. In this video, we are going to see that there's a map in the opposite direction, taking an affine variety and producing an ideal. And then we're going to study, like, how do these two maps interact with each other? And writing down the definition is not so hard. So in fact, we can take any subset X inside AN, and then we define I of X, the ideal or the vanishing ideal of X, just as the set of polynomials which vanish at all points of your subset X. And to justify why we're allowed to call this the vanishing ideal, we can quickly check that this is an ideal in the polynomial ring here. And the idea is just, for example, if you have f1 and f2 functions which vanish on this set X, and you take their sum, the sum still vanishes on X. And similarly, if you have g any polynomial and f a function vanishing on X, then if you multiply them, well, this term is 0, and so the product is also 0 at all points of X. And so this ideal is invariant under the usual operations. And there's some very basic properties that are really easy to check and similar to the properties that we saw for the vanishing function, namely, well, if you have x1 subset x2 in AN, then the ideal of functions vanishing on x1 is possibly bigger and at least contains the ideal of functions vanishing on x2. This is the proof is exactly similar to the corresponding thing of the vanishing functions, just using that. Well, now the conditions that we impose is you have to vanish at points of AN. And so if x2 has more points, then you impose more conditions. And so the ideal of functions vanishing on this set is contained in this ideal. So again, the inclusion is reversed. And then we did see last time that the radical of an ideal showed up. And we did see that the vanishing locus of the radical of J is equal to the vanishing locus of J itself for J in ideal. And here, what we can observe is any ideal of the form I of X for a subset X in AN is actually automatically a radical ideal. To just see this, I mean, one inclusion, any ideal is contained in its radical. So this inclusion here is always satisfied. So for the other inclusion, if f is in the radical ideal of I of X, then by definition there exists m greater equal 0 such that f to the m is in the ideal of X. But then f to the m being in here just means, well, this equation is satisfied. F of x to the m is 0 for all x in your subset. But again, we work over fields, so the power of some element is 0 if and only if the element itself is 0. So we can get rid of the power, but then this equation here is just equivalent to f being in the ideal of x. So we see that all of these things are radical ideals, and this will come up in a second. But now we can just see that we did produce an arrow in the opposite direction, because in particular, we can take X to be an affine variety. This produces an ideal. And the question now is, for this correspondence, what happens if we first go one way, then the other way, in the two possible combinations? And this is an important theorem, and this is Hilbert's Nullstellensatz. So it says that for any affine variety x, so we start here, we have that we first go this way, then this way. So we take I of x and then the vanishing set. Then this here just reproduces the set x itself. So it's starting to look like maybe this is the bijection, but then the second part is a bit more subtle. If we start with an ideal, and then first take the vanishing set and then the ideal of functions vanishing on it, then we don't necessarily get J, but we get the radical of J. So something happens there, but it means if we want to have a bijection, we just need to slightly restrict which ideals we look at. So in other words, if we take inside the set of all ideals, so this here would be the diagram above. If we take the subset of all radical ideals, then by the remark here, we saw any ideal of the form I of x is a radical ideal. So in fact, this I factors through the subset. And then once we restrict to the subset, this actually becomes a bijection, because now if you start with the radical ideal J and then go vanishing and then ideal, then you get the square root of J, which by definition for a radical ideal is J itself. And so here on this horizontal level, I and V are now inclusion reversing bijections. And just from a high vantage point of view, that's really nice, because it tells us we have a correspondence between these kind of geometric objects, these affine varieties, these solution sets, and something in commutative algebra, namely the radical ideals. And that means we're going to exploit this, and basically whenever we have a result in commutative algebra, we can then translate it to a result about these geometric solution sets. Okay, and for the proof of this Nullstellensatz, there's kind of two equalities. Each one you can prove by two inclusions, and it turns out 3 of the inclusions are very easy, and then 1 you have to work for. Let's see the easy inclusions. So let's start with A, the inclusion of x in this left-hand side. Well, if you have x in x, it means by definition of Ix that f of x is 0 for all f in this ideal. But then just take exactly the same statement, then it also implies that x is in the vanishing locus of this ideal. So, I mean, nothing has really happened here. We've just kind of plugged in the definitions. So this is always contained in the vanishing locus. We're going to prove them in a slightly interesting order. Let's first prove the inclusion from here to here. So if f is in this radical, then we want to show it vanishes on the vanishing set of J. In other words, if we have x in the vanishing set of J, then we can use a lemma that we had before, which says the vanishing set here is equal to the vanishing set of the radical. So then, because f is in the radical, in fact, f of x is equal to 0 for all x in this vanishing set, and thus f is in the ideal of the vanishing set. So again, not much has happened except that we used this short lemma. And then for the last part, so here we have A, this inclusion. So we want to say, if something is in the vanishing set of I of x, then it is in x. Now, careful, this would no longer be true if x is any arbitrary subset of an, but this really uses that x is an affine variety. With this we have to plug in. So because x is an affine variety, just by definition, we can write it as v of j for some ideal j. And so then computing v of I of x, we have this is v of I of v of j. Here we plug this in. And now you see we can kind of evaluate this thing here using this inclusion, because at least we know that the ideal of the vanishing set of J contains the radical of J. And then we can use now that the vanishing set reverses the inclusion. So if you have this contained in here, then the vanishing set here is contained in the vanishing set of square root of J. And then we use the same lemma that we had before, that the vanishing set doesn't change under taking the radical. And then we have simplified this expression to just V of J, but by definition, this was X. And so this shows indeed the vanishing set here is contained in X. So we have 3 of the 4 inclusions. So there's one more left, which is in part B, the inclusion here. It's part B, this inclusion here. So it says the ideal of the vanishing locus of J is contained in the radical. In other words, if a function f vanishes on this vanishing locus, then it's in the radical, so it means there exists some power such that it is actually contained in this ideal. And so here, the good thing is that this algebraic geometry course is right in the semester after the commutative algebra course. And in fact, this was part of the commutative algebra curriculum. So exactly this statement here was actually proven there, and this is what is called Hilbert's Nullstellensatz. And so for now, I can be a bit lazy and can just say, well, this was proven in the last semester. But still, we are going to see some reformulations, some weaker versions of this Nullstellensatz, and see both how they're implied by this and then how you can use this to go further. So for now, I wanted to conclude this video by saying a bit about this correspondence and also seeing like where do different assumptions come in. So first, we should do one concrete example. And so if we're talking about varieties in A1, so n is equal to 1, then everything becomes very explicit. So let's start on the ideal side. So let's take J an ideal in this polynomial ring. Then, again, something from commutative algebra, we know this polynomial ring in one variable over field is actually a principal ideal domain. So this means this ideal here, the principal ideal is generated by a single element f, so a single polynomial in one variable. And then because K is algebraically closed, another characterizing property is that this f then decomposes into a sum of linear factors. So in other words, you can always choose this generator to be just of this form, some coefficient, and then linear factors of the form x1 minus ai to some powers. So this is the one equation that we impose, that this f should vanish. And then, well, when does this thing here vanish? Let's assume that C is not 0, because otherwise we will get just the full set A1 as a solution set. So if the C is non-zero, well, this expression vanishes if and only if one of these linear factors vanishes. And this exactly happens if x1 is equal to ai. In other words, the vanishing locus here is just this finite set A1 up to AR inside A1. And then, so we have now taken the vanishing locus of this ideal, and we can do the opposite. Now we can now we can plug it in to the I function and ask, like, what functions vanish on here? That's a kind of interesting direction of the Nullstellensatz. So if you have a polynomial which vanishes at all of these points, well, I claim that vanishing at A1 is equivalent to being divisible by the linear polynomial x1 minus a1. Simply because if you have a polynomial vanishing here, then you can do polynomial division, And this cannot have a remainder, which is non-zero, and because otherwise it would not actually vanish at this point. And so the division goes through, and so you're divisible by this term x1 minus a1. And similarly for the others. And so in conclusion, this means that the ideal of this finite set here is just all polynomials which are divisible by this product of these linear factors. Again, because it is a polynomial, it's divisible by each of them if and only if it is divisible by this product here. And conversely, it is of course true that this product here also vanishes at all of these points. And so we see what happened. We started with the ideal generated by this thing. Because the constant is non-zero, we can actually omit it. We started basically with the ideal generated by these powers, the product of these powers of the linear factors. And we saw, after going through this procedure, the powers have been removed and we just have this. And this is reflected by the fact that this ideal here is the radical ideal of the ideal generated by this product of powers. So that's one thing. That's the concrete Nullstellensatz in action. The second one, which I wanted to emphasize here, is that it was really important for the Nullstellensatz that K is an algebraically closed field. Because otherwise, if we took, for example, K the real numbers, then we can take the ideal generated by the polynomial x squared plus 1. Now, if we look for real solutions in R1, then, well, this function here can never be 0 because x squared is already non-negative, so x squared plus 1 is always strictly positive. So the vanishing locus of J is the empty set. But then if you apply I of V of J, then, well, the ideal of the empty set, this is the set of all functions such that for all entries of the empty set, they vanish there. Well, the empty set is empty, so we actually don't impose any conditions. So we just get all polynomial functions, all polynomials. But this is not the same as the square root of x squared plus 1. Because in fact, you can check this ideal is a prime ideal corresponding to the fact that x squared plus 1 is an irreducible element of R of x. And the square root of any prime ideal, or the radical of any prime ideal, is actually just the ideal itself. And so we see, well, this is a strict ideal, this is the entire ring. So the claim of the Nullstellensatz is just false if you don't have the assumption of being algebraically closed. So these were some first properties, and the next video is going to see like what other results can we immediately conclude from this Nullstellensatz and why is it kind of useful.